our next speaker, we're very happy to have Kexin Pei here. Kexin is an assistant professor at the Department of Computer Science at U Chicago. He received his PhD also in CS from Columbia. And he's broadly interested in security, software engineering, and machine learning, focusing on developing data-driven program analysis to improve the security and reliability of both traditional and AI-based software systems. So we're very excited to hear your talk on analyzing and optimizing software by both robust and sample-efficient learning.
Okay. Yeah, thanks so much for the introduction, Tian. And yeah, it's my pleasure to be here to introduce our recent research on large language model or machine learning for code. Basically, my background is on security and software security, software engineering, and focus on how we develop data-driven program analysis approaches to build reliable, efficient, and secure software. So yeah, I'm trying to adapt my research to be more related to efficient or efficiency machine learning, but bear with me if it sounds not that related. So yeah, large language model today are transforming basically all the code development, code generation, code analysis, software development. A lot of these very exciting tools have been developed to support software developers like Amazon Q developers, Copilot, Cursor. I'm not sure if you have first-hand experience with these tools. They are indeed amazing. Some reported statistics by big companies like on these code agents, like GitHub Copilot today is writing more than 41% of the code that developers previously manually write. And Google has reported 25%, but my personal experience is the number is even higher than this. And also, I think yesterday, Cloud 4 was dropped by Anthropic. They have this very impressive performance on code agent on, for example, benchmarks like SweBench, where given the GitHub code issue, now the code agent can completely automatically solve the issue without any human intervention. And they have achieved around 80% of the success rate, meaning that out of 5 GitHub issues arbitrarily on GitHub, 4 of them can be now automatically solved by code agent without any developer's expertise. And also, I think last week or this month, Google dropped this Alpha Evolve that also discovered a lot of new efficient matrix multiplication algorithms, which are also very exciting. So all of these evidences are amazing, right? It seems that soon coding agents will take over software development, where all the developers might lose their job. But is this really the case? Still, there are a lot of hard challenges in machine learning for code in general. So we have such a powerful tool to create a lot of code for us, but this kind of code usually suffers from inefficiency, or sometimes they are not even secure, they are not readable, a lot of correctness cannot be guaranteed. A lot of other issues beyond just generating the code still exist. So in this talk, I will try to explain our recent work on how do we further support software maintenance beyond code generation or software creation to further optimize the efficiency of this generated code. Of course, we also focus more on insecure code that we want to make it more secure, but for this talk, I will focus more on code optimization. Another critical issue is that people also use machine learning or large language model to not only write the code, generate the code, but also analyze the code in order to detect, let's say, software vulnerabilities or detect malwares or try to fix some bugs or the patches. And turns out that if you're using machine learning instead of traditional compiler approaches to do this, they suffer a lot of problems like inefficient learning, because software programs are not like images or natural language, right? Where a lot of the rules or semantics of the code are very well defined, precisely defined. So it turns out that if you're using machine learning for code, you're still representing the program as some form of natural text and try to ask the model to rediscover a lot of already well-defined rules in the software. It is super inefficient. Why don't you build this knowledge directly into the model instead of using the model following these data-driven approaches and relearn these rules that people have already defined? So that's why I also, if I have time, I also try to introduce some our previous work on incorporating this inductive biases or structural biases of software as this group equivariant kind of property represented as a code symmetry, such that we can build this symmetry preserving code model architectures into existing language models, so that we can achieve sample efficient learning without any pre-training effort. So let me start with the first direction, where it is machine learning for efficient code. And then I will try to jump on efficient learning for code. So this one is on learning code transformation rules for code editing. Just recently got accepted in ICML 2025. I will start with this simple example on code generation. Very typical scenario where, given a problem description, as you can see here, where we want to implement a program to count and print how many of the given heights are greater than or equal to a specified threshold. As you can see here, the sample input, the first line, specifies the number of inputs or number of numbers that user will feed into the program. And the second number, 10 here, indicates the threshold. Now the second line of numbers here is the actual number of digits. Basically, you have 5 numbers as indicated as the first number in the first line. And the task is to count how many of them is greater than the threshold, which is 10. As you can see here, we have 15 and 23, which are both greater than 10. So the expected output will be 2. We have 2 out of 5 numbers that are greater than 10. So now in order to implement this problem description, this is actually a human eval, which is a very popular code generation benchmark. Large language model generates this piece of code.
Which model? Curious.
Old model, GPT 3.5. Yeah. Yeah, did you see any opportunities for optimizations for this piece of code? There are several inefficient implementations in this piece of code.
2 for loops.
2 for loops. Yeah, perhaps they can be further optimized, but the patterns, inefficient patterns here are even more obvious.
It is storing everything in a vector while it is
Yeah.
Why do you need to sort them? You just need to find something that's above the threshold.
Yeah, that's one obvious where the sorting algorithm here is totally unnecessary, right? Another is maybe some high-level syntactic features, like here, we use C-in and C-out, which is less efficient than scanf and printf usually in C and C++. The second is, as you mentioned, we're calling the sorting algorithm, but we don't need the array to be sorted in order to count how many numbers are greater than 10. We just simply need to iterate all the numbers once, right, and compute. So now, given such a inefficient generated code, a direct task for using large language model to further optimize this code is that we can basically just prompt the model again, right? Saying, could you please optimize the following code to make it run faster? So this is actually what GPT-4 returns to optimize this piece of code if you do simple prompting. As you can see here, it still keeps using this inefficient I/O functions. Maybe it is conservative. It wants to respect what the developer wants to write. It still keeps this unnecessary code. And even more serious, it attempted to optimize this loop condition, like within the loop. However, this actually breaks the functionality of the original code. It basically moves this if condition check into the loop condition. And now the optimized code is no longer correct, not to mention whether it is efficient or not. So, yes.
Instead of passing the code, you could just pass the initial prompt and then say, make sure to implement it in the most efficient way, right? Because now the GPT basically loses the track of the optimal objective because you're only passing the code, right?
Right, that's a good comment. But usually if you think about the actual scenario of code optimization, your input is usually not the original problem statement. They should not be assumed available. So if you think about the daily software development process, where you are only given a piece of code and you try to optimize it. Right.
There needs to be some specification, right? Otherwise,
Yeah.
it's not always. It's always.
That's a good comment. Basically, given the original code, the model actually implicitly understand or should reason about the code's original intention or semantics in order to preserve that when making the code edit. Right. So those are all challenges. Yep.
I think the main problem here is that GPT-4 is too conservative because it thinks that that is your code, not another previous code that has been generated. So maybe adjusting the temperature or prompting that this is not a correct code or something like that to let GPT decide on changing some stuff can help.
Yeah, exactly. This might be a very simplified baseline where you can further optimize it with chain of thought or any kind of prompting tricks, but still will show that it is not good enough, basically.
From user's perspective, you don't actually put those parameters, right? You just, like in cursor, you just like highlight the code and send to chat and then ask, refine this code.
Yes,
There's no
right.
parameter for users to tune. That's, yeah.
The parameters in terms of
Like temperature, all those.
yes, correct. Yeah, you can build in that as like something behind the scene, right? Yeah, but still, there are always better ways to do that, and we'll try to show one, right? So indeed, here are some existing works people have been trying to leverage large language models to optimize code. If you look at the whole landscape of code optimizations, classically people still resort to compiler techniques where the code is translated to low-level intermediate representations and a lot of optimization opportunities emerge at that level. And of course, transformation at that level ensures correctness. And also it is very conservative, but still it gives you a lot of optimization opportunities. However, in this work, we treat this line of work to be complementary at the compiler level because the transformation is rather restricted. And if you think about daily human refactoring of the code, they usually operate at the source code level. That actually implies there are a lot of opportunities that only surface at the source level that can still give us some opportunities to optimize the code. For example, here, a specific choice of different function calls, compiler would usually not optimize it because it wants to ensure correctness. It wants to be conservative. And also, by making unnecessary function calls, maybe the compiler thinks it has some side effect, so it does not decide to remove it. But at the source code level, it becomes obvious to be optimized. So we still think there are complementary opportunities to optimize code at source level, mimicking what software developer will do to refactor their code. But still, as many of you have already noted, a lot of challenges exist that we need to represent the code semantics or some other rules of how this code should be transformed. And if you notice how machine learning was applied to optimize code at the source code level, you may be amazed by how shallow and trivial they are currently doing, probably because large language model has recently just emerged and traditional machine learning model was not very good at it. They usually follow this end-to-end fine-tuning, where you're given a pair of slow and fast code, just train or fine-tune the large language model a little bit more, such that in the future, given a slow code, the model knows how to optimize the code to be faster. Of course, here, by doing this, you are assuming you can internalize this code optimization knowledge, which is usually very discrete, concise, symbolic, into a continuous model weights, right? And you treat this code optimization as some black box internal decision making within the large language model. And that usually leads to suboptimal performance. Of course, people have been also following this test time scaling kind of technique where instead of simply generating a faster code in one shot, they keep refining this generated code until the code converges, such that they pass all the test cases, they have the most improved performance. But usually if you think about actual developer lifecycle, they are not usually come with test cases, or the piece of code you are trying to optimize may not even be executable. They might just be a small piece of function that you need a full complete code in order to execute it. So the key ideas in our work is basically try to make this code optimization steps explicit. We have two challenges. First of all, the model actually does not actually know what are the concise, precise steps in order to optimize the code. And also, as some of you also noted, the model does not know the intended original functionality of the original code, such that it often breaks the semantics. So what we did is we make this rule learning steps explicit before training the model to do the code optimization. So how do we do that? This is a rather complicated figure that I directly screenshotted from the paper. But if you look at the upper row, that is the original end-to-end fine-tuning paradigm, where given the pre-added code, we train or directly prompt the model to edit the code. And the lower part is also very simple. It is doing some sort of chain of thought, right? So given the pre-added code, which is the slow code, we ask the model to first generate the explicit specifications of the original code. It is trying to specify or understand at least reason explicitly about what this piece of code is trying to do, what are the expected input specifications, what are the expected output specifications, and then besides that, the model is also trying to generate what would be the potential editing steps that can be applicable for this particular input code. And then they will try to, based on this generated rules or knowledge, to generate the output code. This still seems very simple, right? It is basically prompting the model to do chain of thought by generating these editing steps. The key part that we observe is that existing models are not actually super good at doing this kind of task without any training. Especially these generated rules are so diverse and not well defined, such that the model is not usually following the instructions that it generates itself. So the key steps here in edit Lord is we break this rule learning and the code optimization as a two-stage learning process. At the first stage, we actually let LLMs serve as this meta rule learner, which serves as an inductive rule by mining the editing knowledge from a given set of input and output code. Basically, given this slow and faster code, we're trying to learn what are the specific rules per sample and try to merge them or summarize and abstract them into a shared common knowledge base. After these steps, we'll try to bootstrap the training samples by manifest this shared knowledge of editing rule per sample, such that each sample will be augmented with not only slow and faster code, but also the intermediate editing steps and functional specifications. So here it becomes, given the meta rule set and slow and fast code, which is XY, we are trying to learn how to manifest this meta shared rule set per sample to augment each sample. Here we have small r, which is the editing rule, and small s, which is the functional specification. Now, after this data set has been augmented with how they should be optimized for each sample, we'll still apply fine-tuning to train the model, not only generate the optimized code, but also generate the functional specification first, the editing rules second, and finally optimize this joint probability optimization to generate the optimized code.
So what's the loss function you use here? What to compare?
Yeah, the fine-tuning is still doing per token loss function, right? Yes. So it is not using any reinforcement learning. So here is some breakdown of the actual rule learning process, where here large language model itself serves as a rule learner or rule optimizer, where given the pre-edit and post-edit code, as you can see here, I'm also doing like a secure code editing, not only the code optimization. The model is first trying to simply add what are the rules that are manifested by this given input and output code, and add to this meta rule set. It is also allowed to prune the meta rule set so that for those rules that are too specific to each sample, it will be removed, because this kind of knowledge is not generalizable or shareable to other samples, right? So it is too specific. It is also allowed to merge such that we can keep our meta rule set to be concise and generalizable at the same time. As you can see here, large language model basically serves as an optimizer, but it is trying to optimize not just its internal weights, but some explicit external rule editing knowledge base. So here, by doing this, we actually end up with around 300 source level editing rules for different kind of tasks. For this talk, I will focus on performance optimization, but we also did something for reverse engineering to help code to be decompiled. That is also a code editing task. Also, we do security hardening, which is like a generating secure code from insecure code. But here for performance optimization, some rules, as you can see at the source level, look like this. Although we have around 300, but here we include the percentage on average that each rule actually improves each sample in terms of the performance. As you can see this, by simply replace CL to printf, the code, there are more than 30% of the code can be optimized. And of course, if you are smart enough, you can replace some dynamic memory allocation that uses heap to static memory allocation such that you can leverage stack for more efficient optimization. Of course, that requires you to pre-compute the array size, but still, turns out that these rules are particularly helpful for code optimization. Here are some results where we evaluate on this Pi dataset called Performance Improvement Editing Dataset. It gives a bunch of slow code and some ground truth optimized code. And we are trying to evaluate whether these base models trained by our edit lord can have improved performance. And we compare to some state-of-the-art baselines, including this fine-tuned dataset, but still on slow and faster code. The metrics we're trying to show here is the number of optimized programs out of K generations, and also the average speed up emulated using the Gen 5 CPU simulator, and as well as the code correctness, because we don't want our generated code to be only faster. It has to preserve the original code semantics. Here are some results where the orange bar is edit lord. Not surprisingly, edit lord outperforms almost always for different models using different metrics against different baselines. Here, we only show the performance optimization results, but there are other results on different applications. You can find them in the paper. So, to summarize, efficient code editing is crucial. It is not just code generation, right? You want to generate or edit code to be more efficient. And state-of-the-art large language model actually don't learn code transformation rules because they are super explicit. They are explainable, not like image editing, which you can only internalize in part of the diffusion models. So the idea of key edit lord is pretty simple. We just want to make this intermediate process explicit and train the model to learn how they perform. And this kind of intermediate process is explicit, discrete, and concise. Yes?
Did you increase the correctness also in addition to the speed up? Because I thought that one of the columns were for correctness, and I thought how we can increase correctness so the LLM is actually understanding the objective and then try to fix the problems inside that.
Right. We have the ablation because we generate not only the editing rules, but the original code specifications, right? Right. So that's why here, as you can see, the last column is on the correctness, and the correctness-wise, we're still outperforming all the state-of-the-art baselines. Yeah.
So the correctness is matched with the generated specification, or there are some ground truths out there?
There are ground truths where you have test cases. Yeah. So basically, the original code already passes all the test cases, a set of test cases provided in the dataset. So you want to ensure your generated code still pass the same test cases. Although that does not provide provable guarantees, but yeah, that's the best we can use. Right? Yes?
Could you expand a little bit on how you fine-tuned it, like what kind of data you use and stuff?
Right, so here, as you can see the format, basically, once we learn the matter rule set, we'll manifest each rule set for the pre-edit code. So now your format is like slow code, the corresponding specification of this slow code, which also described in natural language tokens, as you can see here, and the per code snippet editing rules, and finally the optimized code. So you have 4 components, and here, if you look at the bottom right equation, given x, which is slow code, you are trying to generate the corresponding specification, the rule edit, the editing rules, as well as the optimized code, which is y. So it is still formulated as next token prediction.
How large was your data training set? Because it seems like you're not going to have thousands and thousands or tens of thousands of training data.
That actually is surprisingly abundant. So we have more than 40,000 samples. Yeah, so there is a data set developed by Google called AlphaCode. For each problem, they have like more than hundreds of user-submitted solutions to implement that. Some solutions are slow, some solutions are fast. So they form a natural optimization pair for you to train. So you end up having a lot of pairs. Yeah.
You say that you include the rule set inside the prompt. You say that this is the pre-edit code, these are the specification, this is the rule set, and that. So you are not doing any search on the rule set to find its ones that are actually good for this. Because I think that if you have a large set of rule sets, then the LLM should forget these and just ignore some of them. So currently you are just including all of them.
Right. In terms of data augmentation, we include part of them. Basically, it's a subset of this rule set. As you can see here, we have this manifesting R, big R, to per sample editing rules, which becomes small r. So each sample will have its own customized, specialized rule to be edited. Of course, this can be formulated as a retrieval kind of task, but here we kind of augment the samples by distilling this R explicitly so that we can train the model to generate this R on the fly instead of retrieve this R on the fly. Yes. Right. So here, a very simple application of emerging large language model for code optimization for improving the efficiency of code. Here, if you think about it, I hope to highlight the importance of learning program semantics or learning the meaning of program or different statement for any kind of machine learning for code applications. So for code optimizations, of course, it's obvious that you need to understand how this code behaves, understand what would be the potential side effect in order to optimize the code, right? There are many other applications of machine learning on code, is that you also need to really learn the meaning of the code and their compositional behavior in order to reason about the code behavior, in order to analyze the code, obtain some insights on, there are optimization opportunities, there are vulnerabilities that you can uncover. So program semantics or learning program semantics are foundations of any code generation or code reasoning kind of research. That is also the foundation of building the compiler, right, in order to interpret a given piece of code. So I did a lot of research on binary analysis. Traditionally, it is a particular important topic to analyze and reason about software where the source code is not given. It has a lot of applications in security. And here I want to give you an example why learning program semantics is so critical for program analysis or program understanding kind of task. So here, detecting binary code reuse vulnerability is a typical application of binary analysis, where it can benefit from machine learning approaches. Why? Because usually people formulate this task by given a piece of vulnerable code that you want to use that as a query to search in a very large code base of binary-only firmware. Because this firmware often use outdated third-party libraries. So given such a vulnerable code query as a code snippet, if you can do this very large-scale code search like a retrieval, you can detect potential vulnerabilities or malware as long as they are similar. So this kind of code similarity or binary code similarity has a great application in vulnerability detection. So binary code similarity requires understanding the semantic similarity of two pieces of code. Maybe you can consider this two pieces of code where they are actually similar. They're the binary form, but they are not that hard to understand. If you look at the upper code, it is trying to assign a register with a value 0, right? And then you try to increment the register by 16. Basically, it's 22 in decimal form, the 16 in hexadecimal form. And the lower code is doing the same thing. It XOR the EAX by itself, which has the same effect of setting EAX to be 0. And it subtract this EAX by minus 16, which also has the same effect of increment EAX by 16. So now, the particular or traditional way of doing this binary similarity is to train a machine learning model, take this two pieces of code, and directly predict whether they are similar or not. However, if you train the model this way, the model usually suffers from not generalizable or robust because it does not really understand the execution effect, but resort to some superficial spurious patterns, like they shared some common keywords in order to determine they are similar. That's why at that time, when I was still using ChatGPT, GPT 3.5, when I ask ChatGPT whether this two pieces of code is similar or not, ChatGPT says they are not similar. Why? Because it says subtract a register by minus 16 leads to minus 16 instead of positive 16. So this actually indicates that even this state-of-the-art large language model these days do not precisely or fully understand the semantics of move, XOR, add, sub, so that they cannot really reason about the actual behavior of this code in order to detect whether they are similar or not, but resort to some spurious superficial pattern. Yes?
I was wondering if we really need to understand the semantic of the code, because alternatively we could treat it as a black box piece of code, has some input, get the output. Now we have a workload of input outputs. Two codes are similar. Two codes are the same if their set of input output are the same, and similar based on the Jacquard similarity of these two, right? So
Right.
why do we need to understand this?
That's a good question. I think in classic machine learning like applications, that's the best we can do, right? Because, for example, images, we cannot precisely describe the semantics of arbitrary images. In code, because the nature of applications, if you're doing some approximate task, yes, probably this is the best effort. But if you're doing something that strictly relies on precise semantic reasoning, such as vulnerability detection, malware analysis, if you do not understand the semantics well, you often suffer from a huge number of false positives. So machine learning tools becomes not usable. This also relates to this adversarial attacks, where if your code is changed a little bit, if your model relies on superficial patterns, yeah, it sometimes gets frustrating, right? So I think that's a belief thing. Some people definitely accept this, but yeah, for code reasoning, people sometimes want preciseness. Otherwise, they think, then I don't need a fancy machine learning. I just resort to conservative compiler techniques. So indeed, this kind of observation also extends to source level reasoning. As you can see here, there is a very popular source code analysis task called code summarization. It's called extreme summarization. Given a piece of source code, the task is basically predict a very meaningful function name for this piece of code, describing what this piece of code is doing. This is particularly helpful for developers try to reverse engineer a piece of code or just try to summarize the code for documentation or maintenance kind of facility. As you can see here, it's also an adversarial attack, right? Where you simply swap two statements, like this red line here, which does not change the program behavior or semantics at all. State-of-the-art machine learning model trained to predict function name changes its prediction from run to update. Basically, the model thinks the behavior of the code changed extremely, extensively. So the consequence of this kind of mistakes is basically the model does not have the robustness and generalization by really understanding what this piece of code is doing. So they often overfit to spurious textual features, and they cannot achieve good results when such a distribution shift. So the existing common practice of how to address this problem is via data augmentation. That is very machine learning way of doing it. Basically, you can represent this different type of code transformations, feed those as augmented data, and train the model to teach this kind of transformations does not lead to changed behaviors. There are also some other advanced techniques that try to ground the program static text with some other modalities, like natural language or some specific structures of the program, or even the execution behaviors, such that the hope is the model can still learn the augmented semantics of code behaviors. Again, this kind of approach is still inefficient, right? You are having a lot of knowledge about the program. You express this knowledge as data, try to leverage the model to rediscover or relearn this data. The clear idea is, why can't we inject this kind of knowledge directly into the model instead of following this data-driven approaches by rediscover the same ideas from the data. And of course, even you can express this data, this knowledge in data, the model supposed to learn from this data still does not have any guarantee that they have learned it, right? Otherwise, they still they will be 100% robust against this kind of transformations. So how do we specify code semantics and build this kind of knowledge into ML models respecting it, right? In programming language, unlike images or natural language, we have like a very well-defined code semantics, for example, in this kind of logic rules. And that also serves as the foundation to build the interpreter to compile the program. A classic recent emerging interesting effort is try to do this as neurosymbolic approaches, right? We still respect all the symbolic rules and try to encode that as part of the neural network. However, as long as you are using traditional symbolic approaches for an understanding program, you are essentially bounded by all the symbolic approaches limitations, like fixed point, like you should interpret each statement one by one, and you have to follow syntax, all the sorts. Neural part always introduce some errors. So is there some new language or representation that we can build into the model such that all these rules can be respected without following traditional neurosymbolic kind of paradigm? So we have this preliminary attempt that we want to express this code semantic knowledge as a group theoretic framework so that we can build this code symmetries as with some provable guarantees, such that the model can preserve the semantics without sacrificing performance overhead. And it does improve the sample efficiencies. Am I running out of time?
Yeah, I guess so.
Yeah, so perhaps I can skip some very technical details. But the high-level idea is that we can represent some specific program dependencies as this specific group called automorphism of the program dependence graph. And then we can represent this symmetry group as part of the distance matrix, such that we can directly bias the self-attention layer to be the automorphism equivariant self-attention. And this leverages the original permutation equivariant of the self-attention layers without precisional embeddings. Here we further bias it so that it can respect code semantics with provable guarantees. So here, of course, the result is good. And we have provably guaranteed violation, 0% violation rate, while having much higher accuracy than the state-of-the-art baselines, which are pre-trained for 2 weeks, and we don't pre-train our model at all. We train the model from scratch, just like the normal fine-tuning effort. So this kind of result is significant, but as you can see, we only support permutation equivariance. There are a lot of code transformations that go beyond permutations, and we do show improved generalization, although no longer provable guarantees. So yeah, that's all. If you summarize, it's basically efficient learning for efficient code, and we try to show one application of improving code efficiency and another application to show improved learning efficiency for code. Yeah, that's all. Thank you so much for your patience.
Any questions from the audience?
Have you tried multi-agent LLMs for the code generation and make it more efficient, or like have you envisioned basically implementing your work?
Yes, we do have tried, because generated code always lacks some correctness guarantee. So we leverage multi-agent kind of framework, but set some agent to be actually, I would say, rule-based agent that can really serve as a, provide correctness guarantees as part of this generation process. Yeah.
Right. So how does it compare against, for example, AutoGen's code generator? Because if I'm not mistaken, they also have some sort of a verifier, a generator and a verifier. So I saw some similarities at least.
Right. So the application we have is like some unique formulation where instead of like generate the code itself, we are generating the specifications. So basically, we're trying to generate some abstract description of the program behavior as assertions. Yeah. So we are generating assertions and try to interact with like approvers, symbolic executions, so that the correctness guarantees provide that way. So yeah, the application is a little different. Yeah. Thanks. Yes.
Did you try SimC with like existing LLMs? Like, is there some ways to incorporate SimC in already like GPT-4?
Right. We are currently working on integrating it for decoder models because it has this here we assume it is encoder so that it is by default equivariant. So for decoder, we do face additional challenges on tweaking those positioning methods.
I have one question. Can in the second part of the talk, can you extend for example, this sim? So you consider it from a group theory, right, perspective, because you have a finite number of symbolic rules, right? So then you introduce a bias terms in a transformer, right, to learn these symbolic relations. So can you extend this, for example, instead of for the semantic codes to the mathematical reasoning? Because in that field of research we have some accepted rules, for example, like mathematical addition or something like that.
Yeah, exactly. We are actually inspired by that line of work where AI for science, that people incorporate a lot of symmetry, like a group theory, to make the model more sample efficiency. So here, I think there are a lot of ongoing works on developing this group equivariant attention layers, convolution layers. So yeah, I see a lot of exciting opportunities there as well.
More questions? Oh, let's then. Thank you for the great discussion.
I think we have lunch now.